Hello everyone. In this video, I will explain what is context-free language and how can we write the context-free grammars. In all my previous videos, we have discussed about regular languages and regular expressions. Remember, we have also proved that there are some languages which are regular. There are some languages which are not regular. That is, we must have some machine other than finite automata accepting it. Such languages are falling under the category of context-free languages. Note down one more point. All regular languages are context-free languages, whereas the reverse is not true. There are few context-free languages which are not regular. So here we will be discussing in this video, I'll be discussing about context-free languages and I'll show you how to write the context-free grammar. For that, first of all, we'll start with the definition. We will see what is the definition of context-free grammar. A context-free grammar is defined with the help of four tuples V, sigma, S and P, where V and sigma are disjoint finite sets. V is the finite set of variables, also called non-terminals. And sigma is a finite set of symbols. We already know the same sigma we have discussed in the regular expressions or regular languages. S is some element of V. We'll call S is a start symbol. P is the finite set of formulas of the form A arrow alpha. See this, try to understand this A arrow alpha. A is the variable, any element of variable, and alpha is combination of variables and non-variables, that is terminals and non-terminals. That is V union sigma. Whole clean inclusion means any combination of variable and terminal or say constant characters. So we will have formulas A2, that is any variable. On the left hand side of the arrow, we will have a variable. On the right side, we can have any combination of V union sigma whole clean closure. It means we can whole clean closure means we can have a null, or we can have only variables, variable 1, variable 2, or we can have only constants, that is A, B, C, or we can have a combination of variables and constant in any order. So this is the definition. Remember what we have to know. We should know there are four tuples V, sigma, S and P, where V is the set of non-terminals. It has to be finite set. Sigma, we already know it is finite sets of symbols, also called terminals. S is any variable, that is S is the start symbol. We will always start the grammar with symbol S. And P is the finite set of formulas of the form A arrow alpha, where alpha is combination of V union sigma whole clean closure. It means it can have only variables, or it can have only terminal symbols, or it can be null, or it can be any combination of variable and terminal symbols. Note down these points also. We call variables are also called non-terminals. Sigma are called terminals. P is also called grammar rules or productions. The elements of P are called grammar rules or productions. Now we will see some example to write the context-free grammar. Now suppose if we have this x reverse for some x that belongs to a, b whole plus. It means we do not have null strings. X can be any combination of a and b. It is not having a null string. So, and the language has a set of string x followed by reverse of x. Suppose if x is a double b, so reverse of x will be b, b, a. So concatenate x with x reverse, I will get a double b followed by double b a. So what is the pattern of string in this language? whenever there is a starting symbol A, the string should end with an A. Remember, again, the second symbol is B, the second last has to be B. The third symbol is B, the third last has to be B. So accordingly, we have to write the context-free grammar for this. For example, in this case, I will start with S. S can be replaced by A, S, A. Now see this production rule. A is the terminal symbol, S is a variable, and then followed whenever there is an A, it should also end with NA. Starting with NA, it should always end with NA. Similarly, I can write this as if the string starts with an B, it will end with a B. And remember that this language doesn't have a null string. So the smallest possible string I can have is, just see this, the smallest, if x is A, the reverse of x is also A. So the smallest possible string for this case is double A. Or if string x is B, the reverse of this B is also B. So the x dot x reverse, that is concatenated, will have double B. So the smallest possible string in this case is either double A or double B. So at the end I will write this as S is replaced by double A or S is replaced by double B. That's it. So collectively together I can write this context-free grammar as S is A, S A, or this vertical bar is for or, B S B, or double A or double B. So this is the context-free grammar for the given language. All the string of this form can be derived using this grammar. So see the next example. This next example says strings are even length palindrome and sigma is AB. So context-free grammar of this is, we know that string is of what? Combination A and B. So remember that we know that palindrome is of even length, so it will have string of this form, either AA, BB, or A, B, BA, or BAAB, and so on. The strings. Remember that it is even length. I will include null also in this list because null is an even length string and it can be called a palindrome. So remember what we have to do. See the pattern. If the string is starting with A, it is ending with an A. If starting with B, it is ending with B. So I will write it as ASA or BSB, or the smallest possible string is null. So I will write null. So we can clearly see this is an even length palindrome. Suppose I want to derive some string. Now remember that for derivation, I will be making use of this symbol for deriving. So double arrow is for derivation. So suppose if I take some palindrome string of form A, B, B, A, I just want to check whether I am able to derive this string from the given grammar. I'll see that starting with S, I will replace this S with A, S, A, as we have initial symbol A and ending symbol is A. Now this S is a variable. It has to be replaced by any of the production rule in the grammar. So I will now pick B because we need a B here in the string. So this A followed by B, S, B, A. See what I have done? This S is replaced by B, S, B. And finally, I have to replace this S with null. So I will get A double B A. That is the string which is an even length palindrome. Now see this next example. It says that strings of odd length palindrome. that is the smallest string we will have either A or B. So I will write the grammar for this. S can be ASB, ASA or BSB or A or B. Now suppose if I have any string ABA, this is an odd length palindrome. Now I want to derive this string from the given grammar. I will write S is replaced by ASA and this S is replaced by B. So I get ABA. Now suppose if I try to derive any string which is an even length from the given grammar, I won't be able to do that. For example, if I write ABBA and if I do this ASA and then in the next step I want to take ABSBA. Now suppose if I want to replace this S, I will either pick an A or a B. The final terminal symbol would be either A or B because in the grammar we do not have a null string, so I will not be able to generate this even length palindrome. I hope this is clear. So take the next example where strings are palindrome. So now combine the above two, that is even length palindrome and odd length palindrome, then I'll be able to generate all the even length and odd length palindrome strings. So ASA, BSB, A or B or null. So this is the context-free grammar for strings of all kind of palindrome, whether even length palindrome or odd length palindrome, and the strings are on sigma A and B. So therefore, suppose I want to generate any string ABBA. I can do it easily now because we have a null also here. So this will become ASA. Next step, replace this S with BSB. So BSBA. Then next step, replace this S with null. So I get ABBA. Now suppose if I have any string of this form. This is also a palindrome. We can clearly see it is a palindrome. What type of palindrome? Odd length palindrome. So start with derivation of this string ASA. Now this S can be replaced by ABSB. And finally this S is replaced by an A. And an A is in the grammar. So therefore I will write this ABAS. Sorry, this is BA. So I hope these examples are clear how to make the grammar and how to derive the string from the given grammar. Remember, single arrow is used in the representation when we write the grammar rules. Double arrow is used when we are deriving the string from the given grammar. Now let me take any other example. Now suppose this is the example. We have a language a raised to the power n, b raised to the power n. Number of a's are followed by number of b's and the numbers has to be same. And the smallest string we have is this n is greater than equal to 1. It means it is not equal to 0. So the smallest string I will have is a, b. We can clearly see n cannot be 0. So the number is 1, 1. So smallest string I have is AB. Now write down the context-free grammar for this language. Let me start with S. This S, what is the pattern? It says that whenever A is there, B has to be there so that they are matched. So what I will do, A, S, B. Whenever A is inserted, B has to be there in the string. So that they are equal in number. Remember that the smallest string we have is AB. So what I will do, I will write this. Eventually, remember that we cannot leave it like when you're deriving the string from the context-free grammar, we cannot leave the variable as it is. We have to eventually replace with some terminal symbol. And here what is the condition? The language is not having a null string. So smallest, we look for the smallest possible string. What is the smallest string here? As I told that the smallest string is AB. So when smallest string is AB, I will write this as AB here. So I will get this context-free grammar for a raised to the power n, b raised to the power n. Let me take any example. Suppose if I have a raised to the power 3, b raised to the power 3, I want to generate this. So I will start deriving. S is replaced by ASB. 1A, 1B. Take one more step. In the next step, this S is replaced by ASB again. Now we have two A's, two B's. Now what I have to do, I will replace this S with AB because we want 3 A's and 3 B's. So we have A raised to the power 3, B raised to the power 3 string is generated from the given grammar. Now let me take any other example. In the previous example, suppose if I have L is e raised to the power n, b raised to the power n such that n is greater than equal to 0. Now what will be the answer? Look for all the processes same as the previous example. The only difference is that the smallest possible string we can have is null. Null is allowed here because n is greater than equal to 0. So we can have a raised to the power 0 followed by b raised to the power 0. So I will have null dot null, which is null. So null string is there. The smallest possible string is null. So I will just replace the context-free grammar from the above example as S can be replaced by, that is the first rule is ASB, and eventually after having all the derivations, this S can be replaced by null. So this is the context-free grammar for the language a raised to the power n, b raised to the power n for some n greater than equal to 0. So suppose if I want to derive some string of form a raised to the power 3, b raised to the power 3, in this case what I will do, ASB. Again, replace this with ASB. Again, replace this S with ASB. Now we have 3 A's and 3 B's. Eventually this S is replaced by a null. So I will get A raised to the power 3, B raised to the power 3. Now take another example. Here what is the condition? A raised to the power n plus 1 followed by b raised to the power n. It means that we have to write a grammar in such a way that it makes sure number of A's are one more than number of B's, exactly one more than number of B's. All A's are followed by, see the pattern, it says all A's are followed by all B's, and if n is the number of B's, number of A's has to be exactly one more than the number of B's. So I will write the context-free grammar of the form Also note that what is the smallest string? Whenever you have the language to write, do find out the smallest possible string. In this case, if n is equal to 0, because n can go up to 0. So if n is equal to 0, we have a 0 plus 1 b raised to the power 0. So that is the smallest possible string is a. So what I have written here, whenever a is there, b also has to be there, and eventually the variable has to be replaced by a to make sure the exactly one more a than number of b's. For example, if I have some a to b, so we have exactly one a, this is b raised to the power 1, number of a is exactly one more than number of b's. Try to generate this, derive this string from the grammar, this grammar. S is replaced by SB. Now this S is replaced by a single A. So this is double A B. Now take one more example. Suppose if I have A4 B2. Now suppose if I try to generate this, what is this string? The string says that number of A's is 2 more than number of B's. There are 4 A's and I will check whether we are able to generate this string from the grammar, because the grammar is saying that it makes sure that exactly one more A is there in the string. But here we have 2 more A's than B. Let me check if we can derive this. A is B. Again, now we have 2 B's, we have 2 A's. What replacement this S can be? We can replace this S with either ASB. If I do that, I'll get 3 A's and 3 B's. We do not want that. And if I replace this S with single A, this one, this terminal symbol, I'll get 3 A's and 2 B's. So remember that we need to check if the grammar is correct. If we have written the correct grammar, we will be able to generate only the strings of the form given in the language. So we are not able to generate this. We will be able to generate only the strings of the form, the number of A, that is A raised to the power n plus 1 followed by B raised to the power n. Now check this, the second example here. A raised to the power n plus 1 followed by b raised to the power n for some n greater than 0. That is, this time n cannot be equal to 0. The smallest possible value n can have is 1. So what form of string I will have here? A raised to the power n plus 1, b raised to the power n. We have this. If n is equal to 1, so I'll be having this 2 and this. So smallest possible string we have is A square B. The smallest possible string I will have in this language, A square B. So accordingly we need to write the grammar. This is the pattern. Whenever A is there, B also has to be there. The smallest string I will write is double A B. So if this string is there, I will replace S with double AB. Now suppose if we have some string A cube B square, how will you replace this? S is replaced by ASB. Now this S is replaced by double AB. So we have 3 A's followed by 2 B's. That is, number of A's is exactly one more than number of B's. So I hope the examples are clear to all of you. We will be seeing more examples. Now see this example. It says that A raised to the power n followed by B raised to the power m for some m which is equal to 2 times n and n is greater than 0. Now we need to explore what possible strings are there in this language. So let me start with n can take the value greater than 0. Greater than 0. So we have the possible strings, that is smallest value of n is equal to 1. So I will have this 1 and b is 2 times n. 2 times n. So 2 times 1. I'll have this. The smallest possible string in this language is A followed by a double B. So the context-free grammar here would be. And also remember what is the another condition, number of A's followed by B's, and the number of B's has to be 2 times number of A's. Now suppose if we have 2 A's, so we must have 4 B's. If we have 1 A, I will have 2 B's. If I will have 3 A's, I will have 6 B's, and so on. So accordingly, the grammar will become S is replaced by, whenever a single A is inserted into the string, it should be ended with double B's. And eventually, we have already explored that the smallest string is in this language is A double B. So I will write this S can be replaced by A double B. So this is the grammar for the given language. Now take this. It is same. The only difference is that n can go up to 0. So if n can go up to 0, so smallest possible value of n is 0. So if n is 0, m can be 2 times 0 is 0. So that is null is allowed in this case. That is a raised to the power 0, and b is also 0 in this case. So I have a null string. So I get this. The smallest possible string is null here. And we have the same pattern, that is number of a's followed by number of b's, and number of b's are twice the number of a's, 2 times the number of a's. So we will have S is A S double B, or since we know that we can have a null string in this case, so the S can be replaced by a null. Suppose if we have a string is given as A2 and 2 times this value, that is V4. I want to derive this string from the given grammar. I will start with this A S double B. Again, this S is replaced by A S double B, the previous two B's. Now we have already got this double A and 4 times A, 4 times B. So we'll replace this S with null from the grammar. So I'll get this double A 4 times B's. Now try to solve this a raised to the power n, b raised to the power m. And the condition is that number of a's has to be greater than number of b's. Now n is greater than m and m is greater than equal to 0. Now find out the smallest possible string. So m is, the smallest value m can take is 0. And since we know that it says that number of n has to be greater than m, so the smallest possible n can take is 1. So we have smallest string a followed by b raised to the power 0. So the smallest possible string I can have is a. Once I know this, I will try to write the grammar. So what is the grammar? We have to make sure, the grammar has to make sure the number of a's are more than number of b's. So here what we will do, I'll write this S as A S B as we did in all the previous examples. Now I'll take one new variable. Either this S is replaced by ASB or some variable A. Now I have to write the grammar rule for this A. The variable A is having A followed by capital A. I'll explain this, what I'm doing here. And the smallest possible string is A. So I will write this A. That's it. Now what I have done here, this variable capital A is making sure the number of A's are more than number of B's. It could be because there is no restriction that how many more A's has to be there. There is no restriction in the grammar. The smallest number, how many A's are more than number of B's is 1. Suppose there are 3 B's, I must have at least 4 A's. As there is no restriction in the language on how many more A's has to be there, I have to put this loop. we can have any number of A's. Suppose if we have 5 B, I can have 100 A's, or I can have 50 A's, and so on. So this A is replaced by small a, capital A will have any number of A's. Now see this, try to concentrate on this portion. A, capital A. It can derive any number of small a's. See this A can be replaced by AA, that is 1A. Similarly, this A can be replaced by again A, again A, and this A is eventually replaced by this small a. So I will have this 4 A's. I can have any number of A's by having this derivation. So this grammar is saying that A is followed by B, and it is having number of A's are more than number of B's. So try to solve this one. A raised to the power n, B raised to the power n, where n is greater than or equal to m, means now in the previous example it was n was greater than m, but here we can have equality also. So let me try this. If m is equal to 0, what will be the value of n? N can also go up to 0 because it is equal to, equality sign is also there. The smallest value of m is 0. The smallest value of n is also 0. So what I can have, a raised to the power 0, b raised to the power 0. So the smallest string I can have is a null string. So I'll just replace this, the grammar becomes A is B or A. This capital A is replaced by this and null. So I hope this example is clear to all of you. Let me take any derivation such string where number of A's are more than number of B's. Suppose if I take 3 A's and 1 B. So let me derive this as ASB. In the next step, what I will do, this S is replaced by, because I got this 1B, I will now replace this S with capital A, because now I am looking for only the number of A's. So the next step, I will replace this with capital A, the another variable. Now keep replacing A. How many times you want the A? How many A's I want? I will keep calling this AA. So one time I have now 2 A's, 1 B. I will call this AA one more time to get 3 A's. Now eventually I will replace this A with null. So I will get triple A B. Now suppose as we allow n is greater than equal to m, means the equal values of A and B are allowed here in this language. So if I have double A and double B, see how we derive this string from the given grammar. A is B. Now again replace this S with A is B. Now we have 2 A's and 2 B's. Replace this S with capital A. Now replace this A with a null. So I will have double A and double B is allowed in this language. Now I'll just take you back to the previous example and I will try to derive this equal number of A's and B's from the above grammar, from this grammar. Try to generate this double A, double B from this string from the given grammar. Let me check this. First step, replace this with A as B. Now I want it one more time. So I will replace this A as B. Now we have two A's and two B's. I will replace this S with capital A. Now remember that it was, this A is can be replaced by either this value, that is small a capital A, or this terminal symbol A. So that will make sure the number of A's are more than number of B's. So in this case, in this grammar, we cannot have more equal number of A's and B's. So I hope the examples are clear to all of you. Thank you so much for watching the video.